Okay. So we had our test yesterday. Any questions on that? I haven't had a chance to enter them into PowerSchool yet, but you can look on Delta Math to see your grade. And these grades, as always, they include the extra credit from the day before the test. So, so test corrections are due Monday, as always, and that's it for that. Okay. So the next thing we're going to talk about, the next unit, is dealing with circles. So today we're going to talk about angles in circles. So first, we need to do a couple simple definitions. An arc is a piece of a circle. Okay, so if I have a circle like this, for example, I might talk about the piece of the circle from A to B. Okay. And you would call this arc AB. This right here. Arc. And put a little arc over it like that. Now, an inquisitive mind might say, well, why can't you go from A to B this way? Well, that arc AB. This arc AB is actually called the minor arc, which is the shortest way to get from A to B along the circle. And this is actually minor arc AB. If you want to talk about the other way, that's called the major arc, and you actually need an intermediate letter or point to talk about that. Like you have to have a third point over here, C, and then you can talk about arc ACB, and that's indicating if you go from A to B, going through C first. Okay, so that's what this arc would be. Okay. That arc would be major arc. ACB. So if you only use two letters to talk about an arc, it's automatically implied that you mean the minor arc, the shortest arc between those 2 points. That way you don't have to always say minor, major, whatever. It's just shorthand notation. You can just say arc AB. You don't even have to write the word arc. You can just write AB with an arc over it. Okay? And if you said arc ACB like this, then you mean the longer way that goes through point C first. Okay, so that's the first definition. Just wanted to make sure everybody's on the same page with. Second definition is central angle. Is an angle whose vertex is the center of the circle. The sides of the angle are radii. The central angle is an angle whose vertex is the center of the circle. sides are radii. Okay, so if I have circle, this, a central angle, it just has to have the angle part, the vertex of the angle, right at the center, and the sides of the angles of the angle are radii. So let's say the center of the circle is like the point O. A, B. So you'd say angle AOB, central angle of circle O. When you talk about a circle, you just call it by its center. This would be circle O. Okay? So when we talk about an arc then, this, it would be helpful if we could somehow compare arcs. Obviously, some arcs are longer than others in the same circle, right? You could have an arc that's more of the circle than another arc. That's kind of common sense, right? So it turns out that we can talk about the measure of an arc. The measure of an arc is equal to the measure of its central angle. Now, notice this is not the same thing as the length of an arc. The length of an arc would be like if you were to take an arc and straighten it out and measure it with a ruler, like how many inches is it or whatever. That's not the same thing as the measure of an arc. The measure of an arc is more like how much of the circle are we including in degrees, okay? So the measure is always going to be, the units are going to be degrees. The length is going to be more like length of units, like inches or centimeters or meters or whatever. Okay, so these are two different ideas. So I should make a point of that. So this is note. Isn't the length of the arc. We can definitely calculate the length of an arc. We can calculate circumference. It's just some percentage of circumference, right? But this is something different. This is more like what percentage of the actual number of degrees is the arc. Okay, so you could have, for example, a 90-degree arc in one circle and a 90-degree arc in a totally different size circle, and the arcs look different. Like obviously, if it's a little tiny circle, a 90-degree arc would be one thing, and if it's a big circle, a 90-degree arc would be much bigger, but it's still the same amount of the circle. Okay, so that's how you measure arcs. So if the measure of an arc is equal to the measure of its central angle, how many degrees worth of arcs are there in a circle? What? Yeah, 360, because there's 360 degrees worth of central angles, so there has to be 360 degrees worth of arcs. That's an important concept. There are 360 degrees worth of arcs in any circle. like, for example, if I gave you a circle and I told you that the measure of arc AB is 120 degrees, and you had to find the measure of major arc AB, it would be easy, right? You could just subtract from 360, right? So x would have to be 360 minus 120, which would be 240 degrees, right? You have to have a total of 360 degrees. So if this part of it is 120, then this part of it has to be 240. That's kind of easy. Other types of questions they might ask about this is they might give you a central angle and ask you to find the arc, or they might give you the arc and ask you to find the central angle. That's easy too, because they're the same thing, right? So if they said something like, here's a circle, and this is the central angle, and they said this is 50 degrees. What's this? That would be easy. It would have to be 50. Okay. Or what if they gave you a circle and a central angle, and they said this arc over here is 260 degrees. Find the measure of this angle. What would that have to be? 100, right? Because if that's 260, that means this one has to be 100, because together they have to add up to 360, and the measure of a central angle equals the measure of its arc. So this has to be 100 as well. So you can see all the different types of questions. They're all easy, but that's the idea. 360 degrees worth of arcs, measure of a central angle equals the measure of its intersected arc. Okay, another definition is a chord. Chord. This has nothing to do with music. I don't know why they call them both chords, but this is something different. A chord is a line segment connecting 2 points on a circle. Okay, so I could have a circle, this, and a chord would just be a line segment that connects any 2 points, like that. This is AB, and you would say AB is a chord. Now there's one chord that's special, has a special name. What is it? What is it called? A chord that has a special name. The idea is you definitely know this word. It's diameter. A diameter is a special type of chord. What's special about it? Yeah, so any chord that passes through the center of the circle is called a diameter. Okay? Chord. Passing through center of the circle is called diameter. So in this picture, if this is point C, this is point D, this is point O, which is the center of the circle, then you would say CD is a diameter. CD okay? So there's an important fact that deals with chords. And it goes like this. In a circle, I'm going to use kind of like a symbolic notation here. I'm going to say congruent chords and then I'm going to use a double-ended arrow, which means this is true if and only if this is true, right? They both kind of imply each other. So it basically means if you have congruent chords, then you have congruent arcs. And then another double-ended arrow, congruent central angles. So maybe that's a little bit confusing the way I wrote that, but here's what I mean. If I have a circle like this, and I have two chords that are the same length, but different chords. So like, for example, let's suppose I have a line segment connecting these 2 points, and then a second chord over here connecting these 2 points. And these 2 chords are the same length. So what this is saying is, if you have this situation, then the arcs that connect those 2 points are also the same measure. That makes sense. It seems like it should be true, right? Definitely true. And then in addition to that, if you draw angles from the center like this, that angle has the same measure as that angle. And of course, that's true if the arcs are the same, right? Because the measure of the central angle equals the measure of the arcs. So this is kind of a basic fact that definitely looks like it should be true, and it's definitely true. It's saying if you have any one of these 3 things, then all 3 of them are true. So I could have started with the premise that I had 2 central angles that are congruent. Then the chords would have to be congruent, and the arcs would have to be congruent. Or I could have started with the arcs being congruent, same measure. And then I would say that the chords connecting them would have to be congruent, and the angles would have to be congruent. So if you have any one of those 3 things, then all 3 of them are true. That's what the double-ended arrow means. Okay? So the second thing I want to talk about, so this is central angles. Second thing I want to talk about is inscribed angles. So an inscribed angle is an angle whose vertex is on the perimeter of the circle. Vertex is on the circle, and whose sides are chords. Now I said on the circle, and when I spoke, I said on the perimeter of the circle. When you say on the circle, that's really what you mean. You mean on the edge of the circle, okay? This really means on the circle's perimeter. Okay, the circle itself is just that line that curved line that makes up the outside of the circle. The interior of the circle is not the circle. It's the interior of the circle. If you wanted to talk about that whole thing, it's actually mathematically called a disk. Okay, just the outside edge of it is the circle itself. Okay, so if I have a circle, an inscribed angle would be an angle like this. Something like that. It has its vertex right on the perimeter of the circle, and it's made up of two chords. This is not a central angle, right? A central angle, this vertex would have to be right at the center of the circle. This is not a central angle. So it turns out that the measure of an inscribed angle is half the measure of its intercepted arc. Okay? So that's an important fact here. Fact. Measure of an inscribed angle is 1/2 the measure of its intercepted arc. So if I have an inscribed angle like this, ABC, then you would say the measure of angle ABC is 1/2 the measure of arc AC. When you say it's intercepted arc, that really means the arc that's between the sides of the angle. That's what intercepted arc means. It means arc that falls in the interior of the angle. Does that make sense? So there's really two types of problems here. There's types of problems where they give you the angle and you have to find the arc, and there's problems where they give you the arc and you have to find the angle. So if they give you the arc, you just cut it in half to get the angle. If they give you the angle, you double it to get the arc. Okay? Two types of problems. So they gave you the arc, like say this was a 70-degree arc, and this is x, you would say x is half of 70, or 35. And if they gave you the angle, so like say they said this was 80, find this arc, you say x is 160. Because you take half of x, you get 80. So x would have to be double of 80. Does that make sense? Now you might be wondering, like, how is that true? Like, how is it true that central angle equals it and the inscribed angle miraculously happens to be half of it? That seems a little fishy. So we can prove it. I'm not going to do a formal proof, but I'm just going to try and convince you that this is true, so that you don't think I'm doing magic up here and burn me. So here's kind of like a proof. Let's suppose that one side of the angle happened to be a diameter. Okay. So suppose I have an inscribed angle where one side happens to be a diameter. I like that. Okay, let me label some stuff here. So this is A, B, C, and then there's the center of the circle, O. So I could definitely like draw in another radius from C to O, right there. That's definitely doable, right? And then hopefully you agree that we have a triangle here. That's definitely true, right? And this is an exterior angle of that triangle. Yes? But what's true about the exterior angle of a triangle? We have this thing from long ago. It's called the exterior angle theorem. Does anybody remember what that says? It says that the exterior angle is actually equal to the sum of the other two interior angles, the remote interior angles. You guys remember that fact? This angle actually has to equal the sum of these two angles. Yes? So by the exterior angle theorem, I know that the measure of angle AOC equals measure of angle OCB plus the measure of angle OBC. This angle has to equal the sum of these two angles. You remember that from long ago, right? But if you look at what I have here, this is a radius. This is also a radius, so these are the same length. And what's true about an isosceles triangle like this? And its angles. Yeah, the angles opposite congruent sides have to be congruent. So if these two sides are congruent, then these two angles are congruent. So if I label this x, this has to be x as well. So what I'm saying is 2x has to equal the measure of angle AOC. This is x, this is x. That has to equal the measure of angle AOC. Right? So x is really half of the measure of angle AOC. But that's a central angle, which is equal to its arc. Right? So if this is a central angle, which equals the measure of arc AC, then the central angle is half its arc. Does that kind of make sense? Are you convinced? Now, this happened to be a special case. And the special case is that it happened to be a diameter that was one of the sides. Well, if you have one of the situations in which the diameter is not one of the sides, you could just use this fact. Like, for example, suppose I have just a random inscribed angle like this. Definitely neither of those are diameters, right? Well, you could just like draw in the diameter like that and just say, well, this angle is half of that arc. This angle is half of that arc by this thing we just proved up here. So therefore, the whole thing has to be half of that arc. That makes sense, right? It's just sort of like the extension of like arithmetic. This is half of that, and this is half of that, then this has to be half of that. But hopefully you're convinced I'm not doing magic. So the types of problems that you're going to encounter are going to be problems that they either give you the arc and ask you to find the inscribed angle, or they give you the angle and ask you to find the arc. Okay? Now there's variations on that too. Like for example, they might give you a problem that's combined inscribed angles and also central angles. Like for example, they might give you something like this where they say, there's a circle. They might give you a picture that looks like this. And they might say, this angle is 40. Find the measure of this angle. But it's just using the two facts together. You'd say, well, if this is a central angle, it equals its arc. And this is an inscribed angle, so it has to be half its arc. 20. The answer is 20. That's kind of easy, right? I'm almost done. This is a long road day, sorry. There's two other, like, just kind of things that come out of the inscribed angle theorem, which is just the fact that the inscribed angle is half its arc. Two important things. Facts. The first fact is any two inscribed angles that have the same intersected arc. Arc congruent. Seems obvious when you see it written down. Obviously, if an inscribed angle is half its arc, and if you have two angles that intercept the same arc, they have to be the same. But it's a little confusing when you see it in a picture. People kind of forget this basic idea. Like, if you have a picture like this, and you have an arc like this, what this fact is saying is, if you have an angle like that, or an angle like this, these two angles are actually the same because they're both intersecting arc AB. Or I could have a third one that goes like this even. These three angles are all the same measure because they're all intersecting, they're all inscribed, and they're all half of AB. So if this AB happened to be a 60-degree arc, this would have to be 30 because it's half its arc. This would have to be 30 because it's half its arc. This would have to be 30 because it's half its arc. Does that make sense, right? That should definitely be true. Yeah. And then the second thing that's true is that any angle inscribed in a semicircle what does that prefix semi mean? Half. So in a half circle is 90 degrees. Any angle inscribed in a semicircle is 90 degrees. So basically what that says is if I have a circle and then cut it in half, so draw in a diameter, it's saying if I draw any angle that is an inscribed angle connecting this point and this point, like that angle, for example, that's a right angle. Makes sense because its intercepted arc is this. How many degrees are there in a semicircle? 180. So it makes sense that this angle would have to be half of its intercepted arc, which is half of 180. But I could have drawn it like this. That's also a right angle. This is also a right angle, right? That's also a right angle, and so on. Any angle that's inscribed in a semicircle has to be 90 degrees. So that's an important factor number 2. Any questions on that? Okay, so that's it. That's it. The Delta Math assignment is just called something, probably arc measure. That's what it's called. Arc measure. And it just deals with central angles and inscribed angles. Central angles are equal to their arcs. Inscribed angles are half their arcs. Now let's stop it.